Exploring transitions and resonance in RLC circuits. The study of RLC circuits involves understanding the interactions between resistors, R, inductors, L, and capacitors, C, and how they manage electrical energy. These circuits exhibit various behaviors depending on their configuration and the nature of the driving forces they are subjected to. Basic RL and RC circuits. In basic RL circuits, a resistor and an inductor are connected, allowing current to flow and create magnetic fields. Similarly, RC circuits consist of a resistor and a capacitor, enabling the storage of electrical energy as an electric field. Each type of circuit brings unique transient and steady-state characteristics due to the components involved. The source-free RL and RC circuits. A source-free RL circuit relies solely on the initial current or magnetic field energy stored in its inductor. As the circuit's energy dissipates over time through the resistor, the current decreases exponentially, indicative of the circuit's natural response. The complementary source-free RC circuit experiences an analogous discharge of the stored electrical charge in the capacitor across its resistor. Unit step function driven RL, RC, and RLC circuits. When a unit step function is applied to an RL or RC circuit, the system transitions from an initial steady state to a new state because of the sudden presence of energy. This unit step driving force allows for the analysis of how the circuits respond over time, leading to exponential growth or decay in the systems. For more complex dynamics, the RLC circuit includes elements from both RL and RC circuits: the inductor, capacitor, and resistor. The unit step response in an RLC circuit results in oscillatory behavior due to the energy transfer between the magnetic field of the inductor and the electric field of the capacitor. Frequency response and resonance. An RLC circuit can be driven by sinusoidal inputs, which leads to frequency responses influenced by resonance. Resonance occurs when the input frequency matches the circuit's natural frequency, causing maximum energy transfer. The frequency response can be evaluated to understand the behavior of the circuit at different frequencies and configure it for desired signal filtering characteristics. Parallel and series resonance. Parallel resonance unfolds within circuits where inductors and capacitors are aligned in parallel, allowing them to interact such that the impedance approaches infinity, causing minimal current flow at resonance. Series resonance occurs when inductors and capacitors are aligned in series, optimizing conditions for maximum current flow at resonance and minimum impedance. Both types of resonance are critical in designing circuits for specific frequency selectivity. Quality factor, or Q factor, measures the sharpness of resonance and selectivity of the circuit's frequency response. A higher Q factor indicates a narrower and more selective resonance peak, making Q an essential parameter in designing filters and oscillators within electronic devices.